Look up on a clear night, and almost everything you see belongs to a star. The points of light are suns, or they circle suns, held close by gravity and warmed by that steady fire. But a little under 7.5 light-years away, in the direction of the constellation Hydra, there is a world that belongs to no star at all. It has no sunrise. It drifts on its own through the dark, lit only by the faint heat left over from its own birth. This is WISE 855, the coldest object of its kind we have ever found, and the nearest free-floating world to our own. Its temperature sits close to the freezing point of water, cold for a world, and unthinkably warm for empty space. The James Webb Space Telescope has now turned toward it, and the question it raises is a quiet one. What is it like to be a place with no sun? When the James Webb Space Telescope opens its eye on something, the picture is rarely dramatic at first. There is a wide black field scattered with the steady points of distant galaxies and faint background stars. And somewhere in that field, for one particular set of observations, there is a single small glow of warmth. It is not bright. It does not announce itself. If you did not know exactly where to look, your eye would slide right past it. Yet that little smudge of light is one of the strangest places in our whole corner of the galaxy. It is a world, somewhere between 3 and 10 times the mass of Jupiter. It drifts entirely on its own. It has no star to circle, no daylight, no warm noon and cold night. It simply moves through the dark, carrying its own faint heat with it, and it sits closer to us than almost anything else of its kind. Astronomers gave it a long catalogue name, but most of them shorten it to WISE 0855. The full label records the patch of sky where it was found, written out in the dry shorthand of star charts. What matters for our story is simpler. WISE 0855 is the coldest object of its type that anyone has ever found. It is also the nearest free-floating world we know, the closest place to Earth that belongs to no sun at all. You can picture it, in a rough way, by thinking of Jupiter. Take the largest planet in our solar system, the banded giant with its great red storm. Now imagine something a little heavier, but built on the same plan, a ball of hydrogen and helium with an atmosphere of drifting gas and ice. Then take away the sun. Set this world loose in the space between the stars with nothing nearby to light it or warm it. That is close to what WISE 0855 is. A giant sunless world, alone. The phrase that gathers around it is the loneliest place near Earth, and that is not just a turn of words. Loneliness here has a precise meaning. Most objects in the sky are tied to something. Planets are tied to stars. Stars are tied to one another in pairs and clusters, and the great wheel of the galaxy. Warmth, in the universe, almost always comes from a neighbour. WISE 55 has no such neighbour close enough to matter. Its nearest real companion, the Sun, is more than 7 light-years away, a distance so vast that sunlight would take over 7 years just to reach it, arriving as nothing more than another faint star in its sky. So when the Webb telescope turned toward it, it was not chasing a bright spectacle. It was reaching across that emptiness to study a place defined by emptiness. The goal was to read the light of a world that makes almost no light, to learn what its air is made of, how cold it truly is, and what it might be like to stand on a giant that has never known a dawn. That is the journey ahead. We will start with how something so faint and so far was ever noticed at all. From there we will work inward, toward what this world is, why it is alone, and what its quiet glow can tell us about the countless other wanderers that may fill the spaces between the stars. It begins, as these stories often do, with a careful look at a piece of sky that seemed almost empty. To understand how strange and how near WISE 0855 is, it helps to set it among the neighbours. The space around the Sun is not crowded, but it is not empty either. Within a sphere of about 8 light-years, only a handful of systems keep us company, and we know them well by now. The closest is Alpha Centauri, a family of 3 stars a little over 4 light-years away. It is the famous next-door neighbour, the first stop people imagine for any future journey beyond the Sun. Beyond it lies Barnard's star, a small dim red star about 6 light-years off, long studied because it slides across the sky faster than almost any other. Then comes a quieter pair called Luhman 16, 2 cool, faint objects bound together, sitting roughly 6.5 light-years away. Y0855 is the next one out, 55. It rests about 7.5 light-years from the Sun, which makes it the 4th closest system we know. To put that in plainer terms, out of every star and star-like object in our immediate neighbourhood, only 3 lie nearer to us than this lonely world. Just beyond it sits the red star Wolf 359, a familiar name to some, which for a while was thought to be closer than it is. The discovery of Y0855 and its cool cousins quietly pushed Wolf 359 down the list, from 3rd closest to 5th. You can find its place on the sky in the constellation Hydra, the water snake, a long faint sprawl of stars in the southern half of the sky. Of course, you cannot actually see Y0855 there with your eyes, or with any ordinary backyard telescope. It is far too dim for that. But its direction is fixed, a specific address in a specific patch of sky, and that address matters because it tells you where to point an instrument sensitive enough to catch it. 7.5 light-years is a distance worth sitting with for a moment. Light is the fastest thing there is, and it crosses the gap from the Sun to the Earth in about 8 minutes. To reach Y0855, that same light keeps going for more than 7 years. If you could somehow ride a beam of it outward, you would leave the Sun behind, watch it shrink to a bright point, and travel through more than 7 years of darkness before you arrived at this cold giant. And even then, the Sun would not be a sun in its sky. It would be just one more star among many, offering no real warmth at all. This is the heart of what makes the place so lonely. It is near, by the measure of the galaxy, near enough that we count it among our closest neighbours, and yet it is utterly cut off from the warmth that ties most worlds to a parent star. It carries its own small heat through a vast cold, with the nearest fire more than 7 light-years out of reach. That nearness is also a gift. Because Y0855 is so close, it is one of the very few objects of its kind that we can study in real detail. Worlds like it almost certainly exist throughout the galaxy, but most are far too distant and faint to examine. This one happens to drift right on our doorstep. The trouble is that even a doorstep object this cold gives off so little light that finding it at all took a special kind of telescope, one built to see not by ordinary starlight, but by heat. The telescope that first caught Y0855 was not aimed at it on purpose. It found the object the way you might notice a stranger in a crowd, by sweeping its gaze across the whole sky and recording everything that glowed. That telescope was called the Wide Field Infrared Survey Explorer, a name usually shortened to WISE, which is also where the object gets the first part of its label. It launched in late 2009 and set to work mapping the entire sky in infrared light. Infrared is simply light with wavelengths a little longer than the red your eye can see. You cannot see it directly, but you feel it all the time. It is the warmth you sense from a radiator across a room, or from a stretch of pavement after a hot day. Anything with heat gives off infrared, and the colder the object, the longer the wavelength of the glow. This is the key to the whole search. A cold world like Y0855 puts out almost no visible light at all. In ordinary starlight it is essentially invisible, a black gap against a black sky. But it is not without warmth. It still carries the faint heat left from its birth, and that heat leaks out as infrared. To an eye that can see warmth, the object stops being invisible and becomes a dim, telltale glow. The WISE telescope was built exactly for that kind of seeing. To detect such faint warmth, its own instruments had to be kept colder than the things it was studying, chilled with frozen hydrogen so that the telescope's own heat would not drown out the gentle signals from space. From its perch in orbit, it scanned the sky band by band, taking image after image, building a catalogue of hundreds of millions of glowing sources. Most were ordinary stars and distant galaxies, but buried in that flood of data were a few rare objects so cool and so red that they barely registered, showing up brightly only at the longer infrared wavelengths and almost nowhere else. WISE 0855 was one of those. It appeared as a faint dot that glowed in the longer infrared channels and stayed dark in the shorter ones. That peculiar colour, bright in heat and missing in ordinary light, is the fingerprint of something extremely cold. A hot star shines across many wavelengths. A cool, sunless world shines almost only in the deep infrared. WISE 0855 showed that signature about as strongly as anything ever found. There is a quiet irony in how it was caught. The very thing that makes WISE 0855 so hard to see, its low temperature, is also what made the WISE telescope the right tool to see it. An ordinary observatory looking for ordinary starlight would never have noticed it. It took an instrument designed to hunt heat, sweeping the whole sky without favouring any one spot, to stumble across a faint warm dot in the constellation Hydra and record it among the rest. Even then, a single faint dot in an infrared survey is not much. The sky is full of faint dots. Many are distant galaxies, some are flaws or noise, and most are far away and unremarkable. To know that this particular speck was something special and something close, you could not just look at it once. You had to watch it. You had to see whether it sat still, the way a distant background object would, or whether it drifted. And drifting, it turned out, was exactly what it did. A nearby object gives itself away by moving. This is one of the oldest tricks in astronomy, and it is the trick that revealed WISE 0855 for what it was. Hold up a finger at arm's length and look past it at a far wall. Close one eye, then the other, and your finger seems to jump back and forth against the background. Now do the same, but slide your finger slowly sideways, and it drifts across the distant wall, while the wall itself stays put. The stars work the same way. A star far across the galaxy hardly seems to move at all over a human lifetime, but an object close to us sharing our patch of space slowly slides against the fixed backdrop of more distant stars. That slow slide is called proper motion, and a large proper motion is a strong hint that something is near. In 2014, the astronomer Kevin Luhman went looking for exactly that kind of motion in the WISE data. He compared images of the same patches of sky taken at different times, watching for any faint source that had shifted position between one set of pictures and the next. Most points held still, but one cool red dot in Hydra had moved, and moved a great deal, sliding across the sky far faster than a distant background object ever could. That motion told him two things at once. First, the object was close, because only a nearby thing drifts so quickly against the stars. Second, it was almost certainly very cold, because of how it had shown up in the first place, glowing in the long infrared and vanishing in ordinary light. A nearby object that gives off almost no visible warmth is a rare and interesting thing. Luhman had found one. To be sure, he could not rely on the WISE pictures alone. The telescope had recorded the dot at a couple of separate moments, enough to notice the motion, but not enough to nail down everything about it. So the search reached for help from another infrared observatory already in space, the Spitzer Space Telescope. Spitzer took further images of the same spot at later dates, adding more points to the track. With several positions spread across time, the path of WISE 0855 across the sky came into focus, and its swift drift was confirmed beyond doubt. It is worth pausing on how ordinary this method is, and how powerful. There is no exotic trick here, no single magic measurement. There is just careful, patient comparison, one image laid against another, looking for the faint thing that refused to stay still. The same basic idea has been used for centuries to find nearby stars and wandering planets. What was new was the kind of object it turned up. Not a star, not a familiar planet, but a cold, starless giant in our own backyard, betrayed by nothing more than its motion and its colour. Kevin Luhman, it turns out, had a habit of finding the sun's hidden neighbours. The cool pair of objects we passed earlier, Luhman 16, carries his name for the same reason. He had a gift for spotting the dim, nearby things that brighter surveys missed. WISE 0855 was, in a sense, the crown of that work, the coldest and one of the closest of all. But knowing that something moves quickly only tells you it is near. To say how near, and to begin to understand what it is, you need to measure the distance itself. And for that, the same slow drift across the sky hides a second, subtler clue. Speed across the sky tells you an object is close. To learn exactly how close, astronomers turn to a gentler kind of motion, one hidden inside the larger drift. It is called parallax, and it is the same effect as the jumping finger you held up a moment ago. As the Earth travels around the Sun through the year, our viewpoint shifts from one side of the orbit to the other. From these two vantage points, months apart, a nearby object appears to shift its position very slightly against the far more distant background stars. The closer the object, the larger that shift. By measuring the size of the wobble, you can work out the distance using nothing more than geometry. It is the most direct way we have of measuring how far away a star or a cold world truly is. For WISE 0855, that wobble is tiny, because even at 7.5 light-years it is enormously far by everyday standards. Catching such a small shift takes repeated, careful images spread across many months and years. The Spitzer Space Telescope, already used to track the object's motion, did much of this work, returning to the same patch of sky again and again to measure how the cold dot drifted and swayed. Later, the sharp eye of the Hubble Space Telescope refined the measurement further, pinning the position down with great precision. The answer that came out of all this is a distance of about 2 3/10 parsecs. A parsec is just an astronomer's unit for these gulfs, a little over 3 light-years each. 2 3/10 of them works out to roughly 7.5 light-years, the figure we have been carrying all along. What the parallax did was turn that figure from a rough guess into a measured fact, with only a small margin of doubt around it. Knowing the true distance changes everything, because distance is the key that unlocks the rest. When you know how far away a glowing thing is, and how bright it appears from here, you can work out how much light it is actually giving off. A candle across a room and a bonfire on a far hill can look equally bright to your eye. Only when you know how far each one sits can you tell the faint flame from the roaring fire. The same logic applied to WISE 0855. It looks faint partly because it is far, but mostly because it truly is faint, putting out only a tiny trickle of energy. With the distance settled, astronomers could calculate just how little. The number is startling. WISE 0855 shines with only a few hundred millionths of the sun's output, a glow so weak it is almost more an ember than a star. And because all of that feeble light comes out as heat in the infrared, it confirmed once again how very cold the object had to be. So the parallax did double duty. It confirmed that WISE 0855 sits among our nearest neighbours, the fourth closest system to the Sun, and it gave astronomers the firm footing they needed to start asking what it is, rather than just where. A cold, nearby planet-sized world giving off the barest whisper of heat is a tantalising thing. But the word cold has been doing a lot of quiet work in this story. It is time to say plainly just how cold this place really is, and why that single fact makes it so important. We have been calling WISE 0855 cold, but the word deserves a real number, because the cold here is the whole point. Most objects that glow on their own in the night are searingly hot. The surface of the Sun sits at nearly 6,000 Kelvin, hot enough to make it shine fierce and yellow. Even the dimmest, coolest red stars run to a couple of thousand degrees. That heat is what lets them shine in ordinary light. WISE 0855 breaks that pattern completely. Its temperature is not measured in thousands of degrees, or even hundreds above what we're used to. It hovers somewhere close to the freezing point of water. The exact figure has shifted a little as our measurements improved. Early estimates put it near 250 Kelvin, which is well below freezing, around -10 degrees Fahrenheit. the chill of a deep winter night. More recent readings from sharper instruments nudge it a bit warmer, closer to the point where water turns to ice, a few degrees on either side of freezing. Either way, the conclusion is the same. By the standards of stars, this object is astonishingly mild. It is roughly the temperature of a cold morning on Earth. Sit with how odd that is. We're talking about a self-glowing object floating in space, the kind of thing you would expect to be a furnace, and yet you could imagine its outer temperature matching a frosty day in your own town. There is nowhere on its surface you could comfortably stand, and its gravity and crushing atmosphere would be lethal in other ways, but the sheer temperature is closer to a winter walk than to anything we picture when we think of a glowing star. That is why WISE 0855 holds a quiet record. It is the coldest object of its kind ever found. This coldness is exactly what makes it so valuable. For a long time, the coldest worlds astronomers could study up close were the giant planets of our own solar system, especially Jupiter and Saturn, which have cooled over billions of years to well below the freezing point of water. Far beyond the Sun, around other stars, astronomers had begun finding planets too, but the ones they could examine were almost all much hotter, young and still glowing from the heat of their formation, or roasting close to their parent stars. Between those two groups lay a gap. There were the cold, familiar giants at home, and the hot, distant exoplanets far away, with little in between that we could actually inspect. WISE 0855 fell right into that gap. It is cold, like Jupiter and Saturn, but it stands alone in open space, where we can study it without a blinding star nearby. It became the first chance to look closely at a Jupiter-like world, at a Jupiter-like temperature, somewhere other than our own back garden. The cold also shapes how the object behaves in ways we will return to. At such low temperatures, gases that stay invisible and airy on a hot world can begin to condense. Water, which exists only as vapour in the scorching air of a hot planet, can chill into clouds of ice. Other compounds freeze and settle. In a real sense, the temperature sets the weather, and a world this cold may have weather more like a frozen version of Jupiter than like anything around a star. But before we can read that weather, we have to confront a practical problem that the cold creates. A world this faint, glowing only in heat, is desperately hard to see in any detail. For years, that very faintness kept its secrets locked away. Being cold makes WISE 0855 fascinating. It also makes it maddeningly hard to study because cold things give off so little light. The amount of light a warm object releases and the colours it favours both depend on its temperature. A hot star pours out a flood of light across many wavelengths, including the visible colours our eyes evolve to catch. As an object cools, two things happen at once. It gives off far less light overall, and what it does give off shifts toward longer and longer wavelengths, away from visible light and deep into the infrared. By the time you reach something as cold as WISE 0855, almost all of its meagre glow has slid out of the range your eye could ever see, and into the far infrared, the realm of gentle heat. This is why ordinary telescopes, even very large and powerful ones, struggle with it. They are built mainly to gather visible and near-infrared light, the kind that stars produce in abundance. Point them at WISE 0855, and there is simply almost nothing there for them to catch. The object hoards its energy at wavelengths these instruments handle poorly, and it releases so little of it that the faint signal is easily lost. The difficulty showed itself plainly in the early efforts to observe it. One team used a powerful telescope on the ground, in Chile, to hunt for WISE 0855 in a band of near-infrared light just beyond the visible. By the standards of most objects, this should have been a reasonable place to look. But WISE 0855 never appeared. The images came back empty at that wavelength, the world too faint and too cold to register. The non-detection was itself a kind of result, a hard flaw on how dim the object was, but it underscored the basic trouble. In the light most telescopes prefer, this place is essentially a void. there was a further obstacle for any telescope on the ground. Our own atmosphere glows softly in the infrared, and worse, it is full of the very molecules astronomers most wanted to find in distant worlds, things like water vapour. Trying to detect the faint warm signature of a cold giant through a layer of warm, water-laden air above your head is like trying to hear a whisper across a noisy room. The air gets in the way, both blocking and mimicking the signal. A few determined teams still managed early glimpses, using sensitive instruments tuned to a narrow band of mid-infrared light, where Y0855 glows comparatively well. Astronomers gathered the first faint spectrum of the object around 2016. It was a hard-won scrap of light, but it carried real news. Within it were hints of water vapour in the object's atmosphere, the first chemical clue to what this cold world was made of. Later ground-based work added a sign of methane as well. Those early results were precious, but they were limited. They covered only narrow slivers of light, gathered with great effort through the blur and glow of our own air. To truly read the atmosphere of Y0855, to take its temperature properly and sort out its weather and its chemistry, astronomers needed an instrument above the atmosphere, kept cold, and tuned to exactly the deep infrared where this world shines. They needed, in short, the telescope that had not yet flown when Y0855 was found. Before we follow that telescope to the object, though, we should be clear about what kind of thing it is going to study, because Y0855 is neither quite a star nor quite a planet. So far, we have called Y0855 a world, a giant, a cold object. It is time to give it its proper name. Y0855 is a brown dwarf, and a brown dwarf sits in the strange borderland between stars and planets. To see where it fits, start with what makes a star a star. A star is a ball of gas, mostly hydrogen, so massive that its own gravity squeezes its core to enormous pressure and temperature. At the heart of the Sun, that crushing squeeze forces hydrogen atoms to fuse together, releasing the steady torrent of energy that makes the Sun shine and keeps it shining for billions of years. Fusion is the engine. It is what separates a true star, lit from within by nuclear fire, from a cold lump of gas that merely sits in the dark. A planet, by contrast, never comes close to that. Even Jupiter, the heaviest planet around the Sun, is far too light to ignite any fusion in its core. It glows faintly from leftover heat and reflected sunlight, but it has no inner fire of its own. It is, in the end, a large cold ball, kept in its place by the Sun's gravity. A brown dwarf falls in between. It forms the way a star forms, from a collapsing cloud of gas and dust drawing itself together under gravity. It can gather many times the mass of Jupiter, but it never quite reaches the threshold where steady hydrogen fusion can switch on. The collapse stops short. The core grows hot and dense, but not hot and dense enough to light the main stellar fire. So the object never becomes a real star. It is sometimes called a failed star, an object that tried to become a sun and fell short of the mark. That phrase, failed star, is vivid, but it can mislead. A brown dwarf is not broken or wrong. It is simply an object that ended up in the mass range between planets and stars, too heavy to be a mere giant planet, too light to burn as a star. Wise 0.55, with somewhere between 3 and 10 times the mass of Jupiter, sits at the very low end of even that in-between range. In mass, it is barely more than a large planet. In origin and nature, it belongs with the brown dwarfs. Because it never lit a lasting fire, a brown dwarf has no permanent power source. It shines only on the heat of its own making, the warmth generated as it collapsed and compressed early in its life. And because that heat is finite, a brown dwarf does only one thing over the long run. It cools. Slowly, over billions of years, it radiates its warmth away into space and grows colder and dimmer. The oldest and least massive ones grow very cold indeed. Wise 855, cold as a winter morning, is one of the coldest we have ever caught. This is the deeper reason it is so lonely and so dark. It is not orbiting a fire that keeps it warm. It is not burning a fire of its own. It is a cooling ember set adrift, slowly fading. Its faint glow is not the light of a furnace, but the last warmth of a thing that never fully caught. To understand that border between burning and not burning, between star and not star, we need to look more closely at the exact line WISE 0855 failed to cross. That line is drawn by mass, and it explains why a giant like this lights no lasting fire while the sun blazes on. The difference between a star and a brown dwarf comes down to weight. There is a threshold of mass, and crossing it is what lets an object become a true, lasting star. WISE 0855 falls well below that line, and the gap explains its whole quiet existence. Picture a forming object pulling itself together from a cloud of gas. As it gathers mass, its own gravity squeezes its centre harder and harder, and the core grows hotter. If the object collects enough material, the core eventually reaches the temperature and pressure where hydrogen can fuse in a sustained way. From that moment on, the object is a star, with an inner fire that can burn steadily for millions or billions of years. The threshold for this is high. An object needs roughly 75 to 80 times the mass of Jupiter, about 1/13 the mass of the Sun, before it can light and hold that hydrogen fire. Below that weight, no matter how the gas piles up, the core never gets hot enough. The fire never catches, or never lasts. There is a second, lower threshold that matters here too. Around 13 times the mass of Jupiter, an object can briefly fuse a rare, heavy form of hydrogen called deuterium. This is a weaker, shorter-lived kind of burning, not enough to make a real star, but enough to mark a dividing line. By common agreement, objects above about 13 Jupiter masses, which can fuse at least deuterium, are counted as brown dwarfs. Objects below that line, which cannot fuse anything at all, are usually counted as planets. WISE 0855 lives near the bottom of even the brown dwarf range, with a mass somewhere around a few times that of Jupiter. Depending on the exact figure, it sits close to the boundary between the lightest brown dwarfs and the heaviest planets. In practice, astronomers group it with the brown dwarfs because of how it formed and how it behaves, but it is a borderline thing, a giant balanced right at the edge of the definitions. It is in mass much more like a heavy planet than like the Sun. What all this means is that WISE 0855 never had a real engine. Whatever brief deuterium burning it may once have managed, if any, was a flicker long ago, not a lasting source of power. For almost all of its life, it has had nothing to fall back on but the heat of its birth. The Sun, sitting comfortably above the high threshold, has burned hydrogen for over 4 billion years and will burn it for billions more. WISE 0855, sitting far below, lit no such fire and has simply been cooling the whole time. You can think of these thresholds as two doors. The first door, near 13 Jupiter masses, opens the way from planet to brown dwarf. The second door, near 80, opens the way from brown dwarf to true star. WISE 0855 stepped barely through the first door, if it stepped through at all, and never came close to the second. It is a thing of the in-between, a giant heavy enough to form like a star but far too light to live like one. This is why its only light has always been borrowed from the past, from the warmth packed into it when it first drew together. To understand how it can still glow at all, after so long without a fire, we have to look at that leftover heat, the slow fading ember at the core of a sunless world. If WISE 0855 has no fire and no star, you might wonder how it manages to glow at all, even faintly. The answer is that it is still warm from being born, and it has not finished cooling down. When any object forms by gravitational collapse, the act of falling together releases energy. Imagine a vast, thin cloud of gas slowly drawing inward under its own weight. As all that material crowds together, it heats up. the same way a gas warms when you squeeze it into a smaller space. By the time the cloud has condensed into a compact object, its interior has been packed and heated enormously. A newborn brown dwarf, fresh from its formation, can be quite warm, glowing a dull red from the heat of its own making. That heat is the only fuel WISE 0855 has ever really had, and heat once made does not vanish at once. It leaks away slowly, radiated off into the cold of space as infrared light. The bigger and better insulated the object, the longer this takes. A brown dwarf wrapped in a deep, thick atmosphere holds its warmth for a very long time, but it always loses in the end. With no inner fire to replace what escapes, the object cools steadily across its whole life, growing colder and dimmer with every passing age. You can picture it as a coal pulled from a fire and set on a windowsill. At first it glows bright and hot. Left alone, it dims to a sullen red, then to a dark warmth you can only feel with your hand, and finally to something no warmer than the room. A brown dwarf does the same thing, but on a scale of billions of years rather than minutes. WISE 855 is far along that path. It is no longer a glowing coal. It is closer to the dark, barely warm ember near the end, giving off only the faintest heat, detectable across the light years only because we built instruments sensitive enough to feel it. This slow cooling is why a brown dwarf's temperature is also a rough clock. Two brown dwarfs of the same mass will differ in temperature mainly because of age. The hotter one is younger, still flush with formation heat. The colder one is older, having had more time to fade. WISE 0855 is so cold that it must either be quite old, or quite low in mass, or both. Its chill is a sign of how long it has been quietly losing the only warmth it ever had. There is something almost poignant in this when you sit with it, though the object itself, of course, feels nothing. Here is a world that formed with real heat, that might in its youth have glowed visibly in the dark, and that has spent the long ages since simply giving that warmth back to the emptiness around it. No star ever lit it, no fire ever caught within it to renew it. It has been, from the start, on a one-way path from warm to cold, alone the entire time. And yet that fading ember is exactly what lets us study it. The leftover heat is real, and it carries information. The way that warmth leaks out, the wavelengths it favours, the dips and gaps in its glow where gases in the atmosphere absorb it. All of this is a coded message about what the world is made of and how cold it has become. To read that message properly, astronomers needed a way to sort WISE 0855 among its kind, and that brings us to the cold end of a long ladder of objects, where this world sits at the very bottom. Astronomers like to sort the things they find, and the cool, star-like objects have a sorting system of their own. It runs from the warmer ones down to the coldest, and WISE 0855 sits at the very bottom rung. Understanding that ladder helps make sense of just how extreme this world is. For most of the history of astronomy, stars were sorted by a sequence of letters that ran from hot and blue to cooler and red. The coolest ordinary stars were the red ones, dim and long-lived. For a long time that was where the ladder ended, because nothing colder had been found to glow on its own. Then, as infrared telescopes improved, astronomers began discovering objects cooler than any star, the brown dwarfs, and they needed new rungs to hold them. 3 new classes were added below the red stars, labelled in turn as the L, the T, and the Y types, each colder than the last. The L types are the warmest of the brown dwarfs, still glowing a deep red, with atmospheres thick with mineral dust and metal vapour. Cool down from there and you reach the T types, cooler objects whose atmospheres are rich in methane, the same gas that hazes the skies of the giant planets at home. These are already strange, cold things, far below any true star in temperature. But the ladder does not stop there. Below the T-types lie the Y-types, the coldest brown dwarfs of all, only discovered in any number once the WISE telescope began its all-sky survey. The Y-types are the deep cold end of the sequence, objects with temperatures low enough that their atmospheres begin to resemble those of planets more than stars. Water can start to behave like weather in them, rather than mere vapour. WISE 855 belongs to this lowest class, and not just anywhere within it. It is one of the very coldest Y-types known, placed near the extreme bottom of the whole ladder. If the sequence of stars and brown dwarfs is a staircase running from blazing blue suns down to frozen sunless giants, WISE 08555 stands on the last step before the floor. This placement is not just a label. It tells you what to expect in the object's light. As you move down the ladder from warmer to colder, the chemistry of the atmosphere changes in step. Hotter objects show signs of vaporized metals and dust. Cooler ones show methane and ammonia. The coldest, like WISE 0855, are expected to show water behaving as it does on Earth, and the giant planets, condensing, freezing, perhaps forming clouds. The class is a promise of what the deep cold can do to an atmosphere, and WISE 0855 is the nearest place to test that promise. It is worth remembering how recent all of this is. The coldest of these classes did not even exist as a category until surveys like WISE turned them up. A generation ago, the idea of a sunless planet-mass object glowing faintly in the dark just a few light years away would have been speculation. Now it has a name, a class, and a precise address in Hydra. WISE 0855 marks how far our reach into the cold has come. Sitting at the bottom of the ladder, WISE 0855 raises a natural question about its own past. An object this cold and this alone had to come from somewhere. It either formed on its own, out in the open, or it was born in company, and somehow ended up by itself. Both stories are possible, and sorting between them takes us into the question of how a world becomes a wanderer. A world drifting alone through space, tied to no star, invites an obvious question. How did it get that way? For WISE 0855, and for objects like it, there are two main stories, and astronomers are still weighing which one fits best. The first story is that it was born alone. In this picture, WISE 0855 formed the same way a small star would, directly from a collapsing clump of gas and dust in a stellar nursery. Stars form when great clouds fragment into pieces, and each piece draws itself together under gravity. Usually those pieces are massive enough to become stars. But the same process can sometimes make much smaller objects, clumps that gather only a few times the mass of Jupiter before they stop growing. Such a clump would never gain enough material to become a star, or even to fuse deuterium for long. It would simply collapse into a cold planet-mass object, sitting on its own from the very beginning, having never had a star to orbit. If this is how WISE 0855 came to be, then it is less a lost planet and more a runt of star formation, the smallest kind of object that the star-making process can produce. It would have been solitary from birth, a thing that formed like a star but turned out far too light to shine like one. The second story is more dramatic. In this picture, WISE 0855 did not form alone at all. It began as a planet or a planet-like body around some ordinary star part of a young and crowded system. Then something flung it out. Young planetary systems can be violent, unsettled places, with several large worlds tugging on one another through gravity. In such a system, close encounters between giant planets can sling one of them outward with enough speed to escape the parent star entirely. The ejected world would be cast into interstellar space, severed from its sun, doomed to drift forever between the stars. If that is WISE 0855's history, then it is a true exile, a planet that once had a star and a place, and lost both in some ancient gravitational accident. It would carry no memory of the event, of course, but its whole lonely existence would trace back to a single violent slingshot long ago. The trouble is that, from the outside, the two stories can be hard to tell apart. A cold giant born alone and a cold giant thrown out from a system can look much the same once they have drifted for ages and cooled down. Clues can come from the object's exact mass, from its makeup, and from the company it keeps or fails to keep. Very low-mass wanderers are thought more likely to be ejected planets, while somewhat heavier ones may be runts of star formation. WISE 0855, low in mass and utterly alone, could fit either tail, and astronomers have not closed the case. What is clear is that both paths are real, and both happen across the galaxy. Some sunless worlds are born solitary, others are made solitary, kicked out of the homes where they formed. Either way, the result is the same kind of object, a cold giant adrift with no star. The ejection story in particular hints at something larger. If young systems really do fling worlds into the dark on a regular basis, then the space between the stars should be littered with such castaways. That possibility opens the door to a whole hidden population, and to the question of just how crowded the lonely dark really is. If WISE 0855 was thrown out of a young planetary system, it would not be unusual. The process that could have exiled it seems to be common, and it may have filled the galaxy with wandering worlds. To see why, it helps to look at how chaotic a newborn planetary system can be. When a star forms, it is wrapped in a disk of leftover gas and dust, and from that disk planets take shape. In the early days, this is a busy and unstable place. Several large planets may form close together, and they do not always settle into neat, well-spaced orbits. Instead, they tug on one another, their gravity nudging and pulling, slowly building up to sharp encounters. When two giant planets pass close, the exchange of energy can throw one of them into a wild new orbit. Sometimes that new orbit is so stretched that the planet is flung clear of the star altogether, hurled outward fast enough to never return. This kind of gravitational slingshot is not rare or special. It appears to be a natural part of how planetary systems sort themselves out. Our own solar system may well have shed worlds this way in its youth, casting smaller bodies, and perhaps even a planet or two, into the dark long before the planets we know settled into their present paths. We will likely never know how many siblings the Earth's family lost in that early reshuffling, but the model suggests the number need not be 0. Multiply that over all the stars in the galaxy, and the implications are striking. If even a fraction of young systems eject one or more worlds, then over the long history of the Milky Way, the spaces between the stars should have collected an enormous number of free-floating planets. They would not be easy to see, being cold, dark, and far from any light. But they would be out there in vast numbers, drifting silently, each one cut loose from the system that made it. There is real evidence that this happens at scale. Astronomers studying nearby young star-forming regions have turned up surprisingly large crowds of free-floating planet-mass objects, far more in some places than the simplest birth-from-collapse models predicted. In one well-studied region, a survey found dozens upon dozens of such objects loose among the young stars, more than could easily be explained by direct formation alone. The excess pointed to a second source feeding the population, almost certainly the ejection of worlds from forming systems. In other words, both birth alone and being cast out seem to contribute, and together they may produce wanderers in great abundance. This reframes WISE 0855 in an important way. It is not a freak, a single oddity that happened to drift near the Sun. It is the closest and best studied member of what may be a huge, mostly invisible population spread throughout the galaxy. The lonely giant in Hydra is likely just the one near enough for us to examine, standing in for countless others too distant and too faint to see. If that is true, then a strange conclusion follows. The dark between the stars may not be as empty as it looks. It may be quietly full of sunless worlds, far outnumbering the bright stars we actually see. But how would we ever count things that give off almost no light? That problem of taking a census of the invisible has its own clever solution, one that uses the bending of starlight itself. If the galaxy is full of dark, starless worlds, we face an obvious difficulty. How do you count things you cannot see? They give off almost no light, they hug no bright star, and most are far too faint and distant for any telescope to image directly. And yet astronomers have found a way to sense them by watching for the moments when one of them passes in front of a distant star. The trick relies on gravity-bending light. Anything with mass warps the space around it, and that warping can act like a lens. When a dark, massive object drifts almost exactly between us and a far more distant star, its gravity briefly focuses and magnifies the starlight, making the background star appear to brighten and then fade over days or weeks as the alignment passes. The dark object itself stays invisible, but its passing leaves a clear signature, a smooth rise and fall in the brightness of the star behind it. This effect is called gravitational microlensing, and it is one of the few ways to detect a world that shines no light of its own. By watching millions of stars night after night, survey teams can catch these rare brightening events. Most are caused by ordinary stars passing in front of others, but some are too brief to be stars. A lensing event that lasts only a day or two rather than weeks points to a small, low-mass object doing the bending, a planet-mass body with no star attached. Each such fleeting flicker is the shadow, in a sense, of a free-floating world crossing the line of sight. These surveys have turned up a real and growing collection of such events, and they tell us that starless worlds are genuinely out there in large numbers. Just how large remains uncertain, and the estimates have swung quite a bit as methods improved. Early results suggested there might be roughly 2 Jupiter mass wanderers for every star in the galaxy, a startling figure. Later, more careful work pulled that number down, with some studies finding the heavier wanderers to be less common than first thought. Other estimates, focused on smaller worlds, run higher again, suggesting several free-floating planets for every star. The honest summary is that the count is still being settled. What the different surveys agree on is the basic fact. Free-floating, starless worlds exist in great numbers, quite possibly outnumbering the stars themselves. Whether the true figure is a fraction of a world per star or several per star, the galaxy clearly holds a vast hidden population of these drifters, most of them small and cold, all of them dark. It is worth noting how indirect this knowledge is. We are inferring the presence of entire worlds from brief flickers in the brightness of distant stars, glimpsed only as a dark mass crosses in front of them. We never see the wanderers themselves in these surveys. We only feel their gravity in passing, like sensing someone in a dark room by the moment they block a far-off light. This is exactly what makes Y0855 so precious. The microlensing surveys tell us the wanderers are out there in their multitudes, but they cannot show us what any single one is actually like. They give numbers, not portraits. WISE 0855, by contrast, sits close enough to study directly. It is the one nearby member of that hidden crowd that we can examine in detail, the single drifter near enough to turn from a statistic into a real, knowable place. Out of a galaxy that may hold billions of starless worlds, WISE 0855 has a special claim on our attention. It is the nearest one we know, and in astronomy, nearness is everything, because it decides what you can actually learn. Most of the free-floating worlds the surveys hint at are hopelessly remote. They are scattered across thousands of light-years, detected only as brief flickers or faint smudges, far too distant for any close inspection. You can count them, after a fashion, and estimate their masses, but you cannot study any one of them as a real individual place. They are dots in a statistic, not worlds you can examine. WISE 0855 breaks that rule simply by being close. At about 7.5 light-years, it is the nearest free-floating planet-mass object known, and one of the very nearest objects of any kind to the Sun. That proximity changes its scientific value entirely. A faint glow that would be unreadable at 1,000 light-years becomes, at this short range, just barely bright enough to dissect. The same cold world that hides easily in the distance sits near enough here to give up real detail about its temperature, its chemistry, and its weather. There is another advantage to studying a free-floating world rather than one bound to a star. When astronomers want to examine a planet that orbits a star, they face a glare problem. The star is millions of times brighter than the planet beside it, and its light tends to swamp the faint planet, like trying to spot a candle next to a searchlight. Elaborate tricks are needed to block the star's glare and tease out the dim world beside it. WISE 0855 has no such problem. With no star anywhere near it, there is no overwhelming glare to fight. Its faint light arrives clean, unmixed with any blinding companion. You can point a telescope straight at it and gather its glow directly. This makes WISE 0855 something rare and useful, a cold, planet-like world that can be studied on its own terms, without a star getting in the way. It offers a clear, uncontaminated look at what the atmosphere of a frigid giant is really like, and because it is so cold, close to the temperature of the giant planets in our own solar system, it bridges a gap that had long frustrated astronomers between the cold worlds at home that we can study easily and the distant exoplanets that are mostly too hot or too far to examine well. In a sense, WISE 0855 is a natural laboratory delivered almost to our doorstep. Nature has placed, just a few light years away, an isolated planet-mass world at a temperature we could not otherwise reach, with no star to obscure it. If you wanted to design an ideal object for studying cold, sunless giants up close, you could hardly do better than this. The only thing missing for a long time was an instrument capable of reading its faint infrared whisper in full. That is what finally changed. After years in which WISE 0855 could only be glimpsed in narrow slices of light, a new telescope arrived, one built precisely to gather the deep infrared glow of cold and distant things. When it turned toward the lonely world in Hydra, it could do what no instrument before it had managed. It could read the light of the loneliest place near Earth in real detail and begin to tell us what its sunless sky is made of. The telescope that finally read WISE 0855 in full is the James Webb Space Telescope, and it was almost made for a target like this. To see why, it helps to understand what sets Webb apart from the instruments that came before. Webb is a large telescope that works in the infrared, the same kind of warm light in which WISE 0855 glows. Its main mirror is far bigger than that of the survey telescope that first spotted the object, which means it can gather much more of the faint heat arriving from a cold, distant world. Where the survey telescope could only register WISE 0855 as a dim dot, Webb can collect enough of its light to spread that light out and study it carefully. Just as important is where Webb sits and how cold it is kept. It orbits far from the Earth, well beyond the Moon, in a stable spot where it can stare into deep space without the Earth and Sun crowding its view. A giant sun shield, layered like the pages of a book, blocks the heat of the sun and keeps the telescope's instruments extraordinarily cold. This matters enormously for infrared work. A warm telescope glows in the infrared itself, drowning out the faint heat of the things it is trying to see. By keeping itself frigid, Webb avoids blinding itself with its own warmth and can pick up the gentle glow of objects as cold as WISE 0855. Then there is the range of light it can see. Webb is built to capture a broad sweep of infrared, from the near-infrared, just beyond the reddest light your eye can catch, out to the mid-infrared, deep in the realm of warmth. This range is precisely where a cold world like WISE 0855 releases almost all of its energy. The earlier ground telescopes could only catch narrow bands, and only by fighting through the glow and blur of our own atmosphere. Webb, above the air and tuned across the whole relevant range, can take in the full spread of the object's light at once. To read that light, Webb carries instruments that do more than just make pictures. The most important for this work are its spectrographs, which spread incoming light into its component wavelengths, the way a prism spreads sunlight into a rainbow. One of these instruments works mainly in the near-infrared, capturing the shorter wavelength end of the object's glow in fine detail. Another reaches into the mid-infrared, gathering the longer wavelengths where a cold world shines most strongly. Together they cover the full span of light that WISE-0855 gives off, from the faint near-infrared trickle to the rich mid-infrared glow. This combination is what makes Webb able to do what nothing before it could. It has the size to gather enough light from a faint object, the cold and the location to keep that faint light clean, and the range and the spectrographs to spread it out and read its details across the whole relevant band. For a target like WISE-0855, dim and cold and shining mostly in heat, it is close to an ideal tool. And so, in a series of careful observations, Webb turned its eye to the lonely giant in Hydra. It gathered the object's infrared glow across the full sweep of wavelengths, near and mid, with a sharpness and depth no earlier instrument had reached. The faint whisper that ground telescopes had barely caught became, in Webb's hands, a detailed signal rich with information. The next step was to read that signal, to take the spread out light and translate it into a description of the world. To do that, astronomers rely on a method that turns light itself into a list of ingredients. When Webb gathers the light of WISE-0855, it does not simply take a snapshot. It spreads that light out into a spectrum, and within the spectrum lies a kind of chemical fingerprint of the world's atmosphere. Reading that fingerprint is the method called spectroscopy, and it is worth understanding because nearly everything we now know about this lonely world comes from it. Start with what a spectrum is. White light, like sunlight, is really a blend of all colours mixed together. Pass it through a prism and it fans out into a rainbow, each colour bent by a different amount, so that the single beam becomes an ordered spread from red to violet. A spectrograph on a telescope does the same thing with the light from a distant object, including the infrared light your eye cannot see. It takes the gathered glow and spreads it out by wavelength, laying the whole range side by side so that astronomers can study it piece by piece. The crucial part comes next. When light from a warm object passes through a layer of gas, the gas does not let every wavelength through equally. Each kind of molecule absorbs light at its own particular set of wavelengths, and only those. Water vapour absorbs at one set of wavelengths. Methane absorbs at another. Ammonia at yet another. So when the light from a glowing object passes up through its own atmosphere on the way out, each gas in that atmosphere stamps the light by removing its own special wavelengths, leaving dark gaps in the spectrum where those colours should be. The result is that the spread out light is not smooth. It is notched with dips and gaps, like a comb with certain teeth missing, and those missing teeth are not random. Each one sits at a wavelength that matches a particular molecule. By looking at where the gaps fall, astronomers can read off which gases the light passed through. A dip in the right place means water. A different dip means methane. The pattern of absences becomes a list of ingredients, written in the object's own light. This is the great power of spectroscopy. Without ever travelling to a world, without touching its air, you can determine what that air is made of, simply by reading which wavelengths are missing from its glow. The depth of each gap can even hint at how much of a given gas is present, and the exact shapes can carry clues about temperature and pressure. A single good spectrum is, in effect, a remote chemical analysis of a place light years away. For a cold object like WISE-0855, this method is especially rich, because the cold lets many telltale molecules survive in the atmosphere where a hotter world would have torn them apart. Water, methane, ammonia, and others can all leave their marks. The challenge has always been gathering a spectrum clean and detailed enough to see those marks clearly. The faint, narrow scraps of spectrum from earlier ground telescopes showed only a few of the strongest features. Webb, with its size and its reach across the infrared, could capture the spectrum in full, deep and detailed across the whole range where these molecules leave their fingerprints. When astronomers finally spread out the light of WISE-0855 with Webb and looked for the gaps, the world's atmosphere began to reveal itself. Certain wavelengths were clearly missing, in patterns that matched specific gases. The first and clearest of those patterns pointed to two molecules already familiar from our own solar system, and from the earliest hints gathered years before. They were the signatures of water and of methane, and finding them plainly written in the light was the first real reading of the air on this sunless world. The first clear molecules Webb read in the air of WISE 0855 were water and methane. Both had been hinted at before, in the faint scraps of spectrum gathered from the ground. Webb confirmed them cleanly and in detail, and in doing so gave us the first solid description of what this lonely world's atmosphere actually contains. Water comes first, because it is the molecule everyone watches for in a cold world. We tend to think of water as something special to Earth, but in fact water is one of the most common molecules in the universe, built from two of its most abundant ingredients. The atmospheres of the giant planets carry it, and so do many stars and brown dwarfs. On a hot world, water exists only as vapour, an invisible gas mixed into the air. On a cold world, it can do more, and WISE 0855 is cold enough for water to start behaving the way it does on Earth. In the spectrum, water vapour leaves a strong and recognisable pattern of gaps, and that pattern showed up plainly in Webb's reading of WISE 0855. The earliest ground-based spectrum years before had already caught a whiff of those water features in a narrow band. Webb confirmed them across a much wider range, removing any doubt. There is water in the air of this sunless giant, the same molecule that fills Earth's oceans and clouds, present in the atmosphere of a world more than 7 light-years away with no sun at all. Methane is the second clear ingredient. Methane is a simple molecule, a single carbon atom bound to 4 of hydrogen, and on Earth it is a humble gas, the main component of the natural gas we burn. In the wider universe it is a marker of cold. The atmospheres of the cool giant planets in our own solar system are rich with it, and it is the gas that gives the coldest brown dwarfs much of their character. Its presence is expected in any world this cold, and Webb duly found its fingerprint in the spectrum of WISE 0855, just as ground-based hints had suggested. Finding water and methane together does more than fill in a list. It confirms that WISE 0855 really does have the kind of atmosphere expected of a very cold, Jupiter-like world. These are exactly the molecules that should dominate the air of a frigid giant, and they are exactly what the coldest brown dwarfs and the cool planets at home display. The lonely world in Hydra, for all its strangeness, turns out to share its basic chemistry with the giants we know best. It is not an alien soup of unfamiliar gases. It is a cold hydrogen world with water and methane in its sky, much like a chilled cousin of Jupiter. There is also a deeper significance in how cleanly Webb read these molecules. The faint, hard-won ground spectra had only caught the strongest features through the blur of our own atmosphere. Webb, above the air and gathering the full infrared range, laid out the water and methane signatures with a clarity that earlier astronomers could only dream of. It turned a few suggestive hints into a confident reading, and in doing so demonstrated that even a world this faint and far could be chemically analysed in real detail. Water and methane, though, are only the most obvious ingredients. They are the strong, clear features that announce themselves first. A cold atmosphere holds more than that, and Webb's detailed spectrum carried the marks of other gases too, fainter but no less telling. Among them were molecules that do more than simply exist in the air. They record the chemistry and the motion within it, and they begin to turn a list of ingredients into a picture of a living, moving sky. Beyond water and methane, Webb's spectrum of WISE 0855 carried the marks of other gases, and 2 of them deserve special attention. One is ammonia, and the other is carbon monoxide. Each tells us something the first 2 molecules could not, about the chemistry of the air and about the way it moves. Ammonia is a compound of nitrogen and hydrogen, a sharp-smelling gas familiar from cleaning products on Earth. In the universe at large, it is another expected ingredient of cold, hydrogen-rich atmospheres, and it shows up in the giant planets of our own solar system. In the coldest brown dwarfs, ammonia becomes an important marker, its features growing stronger as the temperature falls. Webb found ammonia in the air of Y0855, adding it to the world's chemical portrait alongside the water and methane. There is a subtle puzzle in the ammonia though, and it is the kind of detail that only a careful spectrum can reveal. The strength of the ammonia features in Y0855 came out weaker than the simplest models had predicted. The gas is there, but its fingerprint is shallower than expected, as if something is muting it. The same shallow ammonia signature has turned up in at least one other very cold object that Webb has studied, suggesting it may be a common trait of the coldest atmospheres rather than a quirk of this one world. What causes it is not yet settled. It may point to some process in these frigid skies that our models do not yet fully capture. It is a small reminder that even as we read these worlds, they still hold surprises. Carbon monoxide is the other telling find, and its importance lies less in its presence than in what its presence means. Carbon monoxide is a molecule of one carbon and one oxygen, and in a world as cold as Y0855, the calm chemistry of the upper atmosphere should not favour it. In the quiet, frigid outer layers, carbon should mostly be locked up in methane, not in carbon monoxide. By the rules of settled, balanced chemistry, there should be very little carbon monoxide visible at all. And yet, it shows up. The reason this matters is that carbon monoxide tends to form in the deeper, warmer layers of such an atmosphere, well below the cold surface we see. For it to appear up high, where Webb can detect it, something must be carrying it upward faster than the cold chemistry can destroy it. That something is mixing. The churning of the atmosphere that lifts gas from the warm depths to the cold heights and stirs the layers together. The presence of carbon monoxide where calm chemistry says there should be none is a sign that the air of Y0855 is not still. It is being stirred, dredged up from below, kept in motion. This turns a static list of ingredients into something more alive. The water and methane tell us what the air is made of. The ammonia hints that our models are still incomplete, and the carbon monoxide tells us the air moves, that there is weather of a kind on this sunless world, churning its depths and bringing hidden gases to the surface. A frigid, dark giant with no sun to drive it still has a restless atmosphere. Restless air at these temperatures raises the question of clouds. On a world cold enough for water to freeze, the vapour in the sky might not stay vapour. It might gather, chill and condense into clouds of ice. Whether Y0855 truly has such clouds is one of the most stubborn and interesting questions about it, and the answer is not as clear as you might hope. On a world as cold as Y0855, water in the air faces a question that water on a hot planet never does. It can freeze, and if enough vapour chills and gathers, it might form clouds, not clouds of liquid droplets like Earth's, but clouds of tiny water ice crystals hanging in the sky. Whether Y0855 actually has such clouds has been one of the most stubborn puzzles about it, and the honest answer is that we are still not sure. The reason clouds matter so much is that Y0855 sits right at the temperature where they should become possible. Warmer brown dwarfs are too hot for water to condense, so their water stays as vapour. But Y0855 is cold enough that water ice clouds could form in its atmosphere, the way they do nowhere else we can study so closely outside our own solar system. If they are there, this lonely world would be one of the very few places beyond the sun where we have caught water forming clouds, a small echo of the weather on Earth and the giant planets. The early hard-won spectra from the ground hinted that such clouds might indeed be present. When astronomers first gathered a faint spectrum of Y0855 years ago, the best match to its features came from models that included water ice clouds. That result raised hopes that the object was a genuine cloudy world, a frozen sky giant just a few light years away. But the ground-based data were thin, covering only narrow slices of light, and a hint is not a proof. When Webb gathered its far richer spectrum, the picture grew more complicated rather than simpler. Astronomers found that the detailed shape of the object's light could be reproduced reasonably well by models without any clouds at all. A clear, cloudless atmosphere, with the right amounts of water and other gases, fit the data about as well as a cloudy one. So the very feature that the early data seemed to favour became uncertain again. The clouds might be there, but the better data did not require them. Webb's reach into the longer mid-infrared wavelengths added another layer to the story. In that range, astronomers found signs that water vapour grows scarce in the upper atmosphere, thinning out higher up. The most natural explanation is that water is condensing out as it rises into the coldest layers, freezing and falling back, leaving the highest air drier. That is exactly what you would expect if water is forming ice somewhere in the atmosphere. Yet even with that clue, a clear signature of actual ice clouds, the distinct mark such clouds would leave in the light did not stand out plainly. The water seems to be condensing, but whether it builds into true, visible clouds remains unresolved. So the question hangs in a careful balance. WISE JWST is cold enough for water ice clouds. Its water does appear to thin out high up, as though freezing. Some models with clouds fit, but so do some without. The clouds are plausible, even likely in some form, but not proven. It is a genuine open question, the kind that keeps a world interesting, and one that more observations and better models may yet settle. This uncertainty is not a failure. It is what the frontier of this kind of study looks like. We are reading the weather of a sunless world from its faint light alone, and the answers do not always come clean. To make sense of what we do see, astronomers reach for the best comparison they have, the cold giant they understand most thoroughly. That world is Jupiter, and holding Y0855 up against it turns out to be one of the most revealing things we can do. To make sense of a strange world, astronomers reach for a familiar one, and the most familiar cold giant of all is Jupiter. Jupiter is the largest planet in our solar system, a banded ball of hydrogen and helium wider than 11 Earths, wrapped in storms and crowned by its great red oval. It has had more than 4 billion years to cool, and its upper atmosphere is now bitterly cold, well below the freezing point of water. In temperature, makeup, and basic structure, it is the closest thing at home to what Y0855 might be. So when astronomers wanted to understand the lonely world in Hydra, they held its light up against Jupiter's. The comparison turned out to be striking. When the spectrum of Y0855 is set beside the spectrum of Jupiter, the two look remarkably alike, especially in the pattern of gaps left by water vapour. The same molecule absorbing at the same wavelengths marks both worlds in much the same way. In the features that matter most for a cold hydrogen atmosphere, this sunless giant more than 7 light-years away and the familiar planet next door are close cousins. WISE JWST really does behave like a Jupiter set loose in the dark. That likeness is what makes WISE JWST so useful. For a long time, Jupiter and Saturn were almost the only cold giant atmospheres we could study in detail, because they sit right here, easy to reach with our spacecraft and telescopes. Everything else of comparable temperature was either far across the galaxy or hidden in a star's glare. WISE JWST changed that. It offers a second cold giant to compare against the first, one that formed differently, lives alone, and can be studied without a star nearby. 2 examples are far better than one when you're trying to learn the rules that govern these worlds. There are real differences, of course, and they are as instructive as the similarities. WISE is more massive than Jupiter, somewhere between a few and 10 times its weight. It is also somewhat warmer, since Jupiter has cooled further over the ages, and being a free-floating object rather than a planet bound to a star, it formed in its own way, whether alone or by ejection. So it is not a perfect twin. It is more like a heavier, slightly warmer sibling, built on the same plan but raised under different circumstances. The places where the two worlds differ are exactly where the science gets interesting. If Y0855 and Jupiter share so much, then any feature present in one but missing in the other points to something specific about how each world is built and how its atmosphere behaves. A gas that shows up strongly in Jupiter but faintly or not at all in Y0855 becomes a clue, a sign that the inner workings of the two worlds are not quite the same. By comparing them carefully, astronomers can begin to read those differences as evidence about temperature, mixing, and chemistry. And there is one such difference that stands out above the rest. A gas that plays a clear and visible role in Jupiter's atmosphere, but whose presence in Y0855 has become a genuine puzzle. It is a compound of phosphorus, and whether it exists in the air of the lonely world and how much has divided the people who study it. The question of this single molecule turns out to open a window on how calm or how restless the sky of Y0855 really is. The molecule at the centre of the puzzle is phosphine, a compound of one phosphorus atom and 3 of hydrogen. On Earth, it is a rare and poisonous gas. On Jupiter, it is a useful tracer, and it is missing, or nearly missing, from Y0855 in a way that has surprised the astronomers studying it. The story of this one gas reveals how much a single absence can tell you. To see why phosphine matters, look at how it behaves on Jupiter. Deep inside the planet, where the atmosphere is hot, phosphine forms readily. Higher up, in the cold outer layers, it should be destroyed, broken apart and converted into other compounds. So by the calm rules of settled chemistry, there should be little phosphine in Jupiter's visible upper atmosphere. Yet it is there, plainly detected. The only way for it to survive up high is for the atmosphere to lift it quickly from the warm depths before the cold can destroy it. Phosphine in the upper air, then, is a sign of vigorous mixing, of an atmosphere churning strongly enough to dredge gas from below and carry it up fast. Jupiter's phosphine marks it as a restless, well-stirred world. When astronomers looked for phosphine in Y0855, the first careful analysis of Webb's near-infrared spectrum found little sign of it. Unlike Jupiter, this world seemed to show no strong phosphine feature at all. That absence was itself a surprise, and not an easy one to explain since a cold giant like this might have been expected to behave somewhat like Jupiter. The most natural reading was that the atmosphere of Y0855 is calmer than Jupiter's, less vigorously mixed, so that whatever phosphine forms in the depths is destroyed before it can rise into view. A quieter sky, in other words, than the storm-racked giant next door. But the story did not end there, and this is where it becomes a real scientific debate. A separate later analysis of Webb's data, using different methods to tease apart the spectrum, reported the opposite. That work found a small but well-measured amount of phosphine after all, present at a level of about 1 part in a billion. By this reading, the gas is there, just in a modest quantity. The two analyses, drawing on overlapping data, reach different conclusions about whether one of the key molecules is present at all. This is worth sitting with honestly, because it shows how science actually works at the edge of what we can measure. Wise. 855 is faint, its spectrum is hard won, and reading the faintest features pushes the data to its limits. Different teams, making different assumptions, can disagree about a subtle signal. The presence or absence of phosphine in this world is, for now, genuinely unsettled. We do not yet know for certain whether its sky is calm or stirred. What is not in doubt is why the question matters. Phosphine is a window into motion, whether it is absent, telling of a quiet atmosphere, or faintly present, hinting at some mixing. The answer speaks to how the air of this sunless world moves, and that uncertainty drives astronomers to look harder and to seek other clues that do not depend on a single faint gas. Some of those clues come from a different kind of fingerprint entirely, not from which molecules are present, but from the precise variety of atoms that make them up. Most of what we have read in the light of Y0855 concerns which molecules fill its air, but hidden inside those molecules is a finer kind of information, written in the exact types of atoms they are built from. One of the most remarkable things Webb did with this world was to read that finer detail, measuring a rare, heavy form of hydrogen, and doing so for the first time anywhere outside our own solar system. The heavy hydrogen is called deuterium. Ordinary hydrogen, the most common atom in the universe, has the simplest possible nucleus, a single particle. Deuterium is the same element with one extra particle added to its core, making it about twice as heavy while behaving chemically almost the same. It is rare. For every few thousand ordinary hydrogen atoms in the cosmos, only a couple are deuterium, and crucially, deuterium was made in the first minutes after the birth of the universe, and has been slowly used up ever since, never replenished in any great amount. The ratio of deuterium to ordinary hydrogen in an object is therefore a kind of birthmark, a clue to where and how that object formed. Measuring this ratio in a distant world is extraordinarily hard, because deuterium is so scarce. The trick astronomers used was to look not for deuterium alone, but for a special version of methane. Methane, the simple carbon hydrogen gas already known to fill the air of WISE 0855, occasionally forms with one of its hydrogen atoms replaced by a deuterium atom. This heavy methane absorbs light at slightly different wavelengths than ordinary methane, leaving its own faint set of gaps in the spectrum. By carefully comparing the marks of heavy methane against the marks of normal methane, astronomers could work out how much deuterium the world's hydrogen contains. Webb's detailed spectrum was good enough to catch this faint difference. From it, astronomers measured the ratio of heavy to ordinary hydrogen in the atmosphere of WISE 0855. It was the first time such a measurement had been made for any object outside our solar system, the first reading of this primordial birthmark in a world beyond the Sun's family. A quantity that had only ever been measured for the planets and bodies near home was now measured for a lonely giant more than 7 light-years away. The value matters for understanding the world's history. The deuterium-to-hydrogen ratio carries hints about the gas the object formed from and the conditions of its birth. Comparing it to the ratio found in the Sun, in Jupiter, and in the wider galaxy lets astronomers place WISE 0855 in the larger story of where its material came from. It is a thread connecting this isolated drifter back to the chemistry of the early universe and the cloud that made it. There is something fitting in this. Deuterium is left over from the very beginning of everything, a trace of the universe's first minutes still carried in the hydrogen of every world. To find it in the air of the loneliest place near Earth, and to measure it there for the first time, ties this solitary object back into the deep history it shares with all matter. Even alone in the dark, WISE 0855 carries the same ancient ingredients as the rest of the cosmos. The heavy hydrogen was not the only rare atom Webb read in this world. There is a second such fingerprint hidden in the ammonia that tells a related story about origins, and reading it required reaching into the longer wavelengths where only Webb's mid-infrared eye could see. Deuterium is a heavy form of hydrogen. There is a similar trick of nature in the nitrogen of WISE 0855, and Webb caught it. The ammonia in the world's air comes in more than one variety, and the rarer kind carries its own quiet message about where this lonely giant came from. Recall that ammonia, a compound of nitrogen and hydrogen, is one of the gases Webb found in the atmosphere. Most of that ammonia is built from the common form of nitrogen, but a small fraction is built instead from a slightly heavier form, a version of nitrogen with one extra particle in its core. This heavy variety is rare, making up only a tiny share of all nitrogen. Ammonia made with it absorbs light at slightly shifted wavelengths, just as heavy methane does, leaving its own faint signature in the spectrum. Catching that signature took Webb's reach into the mid-infrared, the longer wavelengths where this kind of ammonia leaves its clearest mark and where a cold world glows most strongly. Using the instrument built for that range, astronomers detected the heavy form of ammonia in WISE 0855 and measured how it compares to the common form. From that comparison, they derived the ratio of the two kinds of nitrogen in the world's atmosphere, Another fingerprint of its makeup read from light alone across more than 7 light-years. Why does the variety of nitrogen matter? Because like the deuterium ratio, the balance of heavy to light nitrogen reflects the conditions under which an object formed. Different processes in the galaxy build these isotopes in different proportions, and the mix an object inherits depends on the gas it condensed from and the events that enrich that gas before it. By measuring the nitrogen ratio in WISE 0855, astronomers gain another clue to its origin, another data point in the question of whether it formed like a tiny star or began life as a planet around some other sun. These isotope measurements, the heavy hydrogen and the heavy nitrogen, are among the most advanced things we have learned about this world, and among the angles that simpler accounts of it tend to skip. They go beyond the basic question of what gases are present and into the finer question of exactly what those gases are made of, atom by atom. That level of detail, for an object this faint and this far, would have been almost unimaginable not long ago. It is a measure of how far our instruments have come that we can now read the isotopic birthmarks of a sunless giant in the constellation Hydra. Together, the molecules and their isotopes build a portrait of a world that is at once familiar and strange. Familiar in its main ingredients, water and methane and ammonia, the same gases that haze the giant planets at home. Strange in being utterly alone, lit by no sun, and yet carrying these ancient atomic fingerprints in its air. Each rare isotope is a thread tying this isolated drifter back to the wider chemistry of the galaxy and the early universe. All of these readings, the gases, the mixing, the isotopes, are really pieces of a larger puzzle. Put together, they begin to describe not just what the atmosphere contains, but how it behaves, how it is layered, how it moves, and how it changes. They sketch the outline of weather on a world that has never seen a sun. Put all the clues together, and a picture begins to form of the atmosphere of WISE 0855 as a living, layered thing, with structure and motion of its own. It has weather in a real sense, even though no sun has ever shone on it. The energy that drives that weather comes not from outside, but from within, the last heat of the world's birth leaking slowly upward and outward. Start with the layering. Like any thick atmosphere, the air of WISE 0855 is warmer at the bottom and colder at the top. Deep down near the hidden interior it is hot, still holding the warmth left from formation. Higher up, that warmth thins, and the temperature falls toward the bitter cold of the outer layers, the part we actually see when we read its light. This temperature profile, warm below and cold above, sets the stage for everything else. It decides where gases stay vapor and where they freeze, where chemistry runs one way and where it runs another. The freezing matters most for water. Down in the warmer depths, water stays a vapor, mixed through the air. As that vapor rises into the colder heights, it reaches a level where it can no longer stay gaseous, and it begins to condense, just as water vapor condenses into cloud and rain on Earth. This is almost certainly why Webb found the upper air of WISE 0855 growing dry. The water is being wrung out as it rises into the cold, freezing and falling back, leaving the highest layers thinner in vapor. Whether that condensing water builds into true ice clouds remains the open question we met earlier, but the condensation itself appears to be real. Then there is the mixing, the presence of carbon monoxide high in the atmosphere, where calm chemistry says it should not survive, tells us the air is being stirred, dredged up from the warm depths faster than the cold can destroy it, so the atmosphere is not a still, settled thing. It churns, lifting gas from below and carrying it upward, much as a pot of water on a stove turns over as it heats. The phosphine puzzle bears on this too. If phosphine is truly absent, the mixing may be gentler than Jupiter's. If it is faintly present, there may be more stirring than that absence would suggest. Either way, the world's air moves. There is even the possibility of change over time, of something like passing weather. Cold giants of this kind are known to brighten and dim slightly as patches of cloud and clear air rotate in and out of view, a sign of an atmosphere that is not uniform but patchy, with different regions and conditions drifting across the visible face. Webb's careful, repeated observations of Y0855 were partly aimed at catching such variations, looking for the subtle flickers that would reveal a world with weather systems of its own. Imagine then, standing somewhere in that sky, if you somehow could. There would be no sun overhead, no day or night, only a permanent deep twilight lit faintly from within. The air would be frigid, churning slowly, thick with hydrogen and laced with methane and ammonia and traces of water. High above, water might gather into hazes of ice. It is weather without a sun, driven by the dying warmth of the world itself on a giant that has been cooling alone for ages. A world with weather, with layers and motion and perhaps drifting clouds, is a world worth examining from every angle. And there is one more question astronomers asked of Y0855, a question that reaches beyond the world itself to whatever might be keeping it company in the dark. A lonely world raises a natural question. Is it entirely alone, or might something small be circling it? Planets bound to stars often have moons. A free-floating giant drifting starless through space might in principle carry moons of its own, small companions that followed it into exile or formed alongside it. Astronomers used Webb to look, mounting a deep search for any moon or companion around Y0855. The idea is less strange than it first sounds. When a giant planet forms, it is often surrounded by its own small disk of leftover material, and from that disk moons can take shape, the way the major moons of Jupiter and Saturn formed around those planets. If Y0855 formed like a tiny star or a giant planet, it too might have built moons in its youth, and if it was ejected from some distant system, it is even possible that a moon or two stayed gravitationally bound to it through the violence of being flung into space, travelling with it ever since. A sunless giant with a faithful moon, wandering the dark together, is a real possibility worth testing. Finding such a moon is extraordinarily difficult, because it would be tiny and cold and lost in the faint glow of the world it circles. But Y0855's nearness gives astronomers a fighting chance, and Webb offers two ways to hunt. One is simply to look, very carefully, for any second point of warmth near the world, a faint companion separate from the main glow. The other is to watch the world's brightness over time, searching for the slight regular dip that would occur if a moon passed in front of it, briefly blocking a sliver of its light. That second method, a transit search, becomes possible precisely because Y0855 is close enough and steady enough to monitor. So astronomers carried out a deep search of both kinds, scrutinizing Webb's observations for any sign of a companion. The honest result is that no confirmed moon has emerged. The search did not reveal an obvious satellite circling Y0855. What it did do was set limits, ruling out companions above certain sizes and narrowing the range of what could be there. Finding nothing clear is not the same as proving nothing exists, but for now the lonely world appears to be just that, without any confirmed moon to keep it company. Even a search that finds nothing is valuable, and not only for this one world. Learning how to hunt for moons around free-floating planets and understanding what such searches can and cannot detect is groundwork for the future. There may be many sunless giants out there, and some of them may carry moons. The methods tested on the nearest example, Y0855, are the methods that will be used on the others as our instruments improve. A moon orbiting a starless planet would be a remarkable thing to find, a small warm world circling a larger one in total darkness, and knowing how to look is the first step toward ever finding one. For now though, the picture holds. Y0855 drifts on its own, a cold giant with no sun and, as far as we can tell, no moon, alone in the fullest sense. That solitude is part of what makes it so striking. But its true importance reaches beyond its own loneliness. This single nearby world has become a key that helps unlock a far larger set of worlds we can barely reach. the cold planets scattered around distant stars. For all that WISE 855 is a fascinating place in its own right, its deepest value may lie in what it teaches us about worlds we can barely see. It sits in a crucial gap between the cold giants of our own solar system and the distant planets circling other stars, and it serves as a bridge between them. Studying it up close helps us understand a whole population of worlds that are otherwise out of reach. Consider the problem astronomers face with exoplanets, the planets that orbit other stars. Thousands are now known, but studying their atmospheres in detail is hard, especially for the cold ones. A cold planet gives off little light, and it usually sits right next to a star millions of times brighter, whose glare drowns it out. The exoplanets whose atmospheres we can examine best tend to be the hot ones, either young and still glowing from formation, or roasting close to their stars. The cold, temperate giants, the ones most like Jupiter, are the hardest of all to study, precisely because they are faint and lost in starlight. This is where WISE 0855 earns its place. It is cold, like those hard-to-study giants, but it has no star beside it to interfere. We can point a telescope straight at it and read its atmosphere cleanly, gathering the kind of detailed spectrum that a cold exoplanet next to a bright star would never allow. In effect, WISE 0855 lets us study the atmosphere of a cold giant world under ideal conditions, free of the glare that hides its distant cousins. What we learn from it becomes a guide for understanding those cousins. The lessons are concrete. By reading WISE 0855, astronomers test and sharpen their models of how cold, giant atmospheres work, how water and methane and ammonia behave at these temperatures, where clouds form, how the air mixes, what the isotopes reveal. Those same models are then used to interpret the fainter, messier data we manage to gather from cold exoplanets. A clear reading of one nearby example helps make sense of many distant ones. WISE 0855 becomes a kind of reference world, a clean example against which harder cases can be compared. It also stretches the range of conditions we can study directly. Before objects like this were found and examined, the only cold giant atmospheres we knew well were Jupiter and Saturn, shaped by their particular histories around the Sun. WISE 0855 adds a different kind of cold giant, one that formed alone or was cast out, at a somewhat different temperature and mass. Each new example fills in the picture of how these worlds can vary, and what stays the same across all of them. The more examples we have, the better we understand the underlying rules. So this lonely drifter is not just an oddity at the edge of the neighbourhood. It is a tool, a natural laboratory delivered close to home that helps us read the countless cold worlds we cannot approach. The same techniques and models tested on it will be turned on faint exoplanets for years to come. In studying the loneliest place near Earth, we're also learning how to study the many cold and distant places we may never reach in person. And WISE 0855 is not entirely without kin. Though it stands alone in space, it has neighbours of a sort, other cold and starless or starlit objects nearby that astronomers study alongside it. Setting them side by side helps reveal what is ordinary about these worlds and what makes WISE 0855 special. WISE 0855 drifts alone, but it is not the only cold, faint object in our corner of the galaxy. A small family of chilly worlds and failed stars lies within a few light years of the Sun, and comparing them helps us see where WISE 0855 fits and what sets it apart. None of them is a true companion to it, but together they sketch the variety of cold objects near home. The nearest of these cold cousins is a pair called Luhman 16, found by the same astronomer who discovered WISE 0858. Luhman 16 sits about 6.5 light-years away, making it the third closest system to the Sun, just nearer than WISE 0855 itself. It is two brown dwarfs bound together, circling each other in the dark. They are warmer than WISE 0855, glowing more strongly, and they are famous for showing clear signs of changing weather, brightening and dimming as patches of cloud rotate across their faces. Where WISE 0855 is a single cold drifter, Luhman 16 is a warmer pair, and studying it has taught astronomers much about the restless skies of brown dwarfs. Farther afield, but still close enough to study, is a world called Epsilon Indi AB, a giant planet orbiting a nearby star. It is one of the coldest planets ever imaged directly around another star, and Webb has examined it closely. Strikingly, it shows the same shallow ammonia feature that puzzled astronomers in WISE 0855, the ammonia signature coming out weaker than the simplest models predict. Finding the same oddity in two separate cold worlds suggests it is a real and shared trait of the coldest atmospheres, not a fluke of one object. This is exactly the kind of insight that comparing neighbours provides. There are others in this growing catalogue of cold worlds that Webb has turned to, distant giant planets at low temperatures, each adding a data point to our understanding. Some orbit stars and must be teased out of the glare. Some, like WISE 0855, float free. Each has its own temperature, mass and history, and each shows its own mix of the familiar cold giant gases. Laid side by side, they reveal both the common rules these worlds obey and the ways individual worlds differ. In that company, WISE 0855 holds a distinct position. It is the coldest of them, sitting at the bottom of the temperature ladder. It is the nearest free-floating planet mass object, beholden to no star. And because it is both cold and starless and close, it offers the cleanest, most detailed look of any of them at what a frigid giant atmosphere is truly like. The others are valuable, but WISE 0855 is, in several ways, the extreme and the benchmark, the coldest clear example we have. Seeing it among its neighbours also restores a sense of proportion. WISE 0855 is remarkable, but it is not unique in kind. It is the nearest and coldest member of a class of objects that surveys suggest are scattered throughout the galaxy, in great numbers. The handful of cold worlds we can study near home are the few we happen to be able to reach. They stand in for a vast population beyond our current sight. That vast population is the real frontier. The cold drifters we can study now are only the nearest examples, and our knowledge of how common they are and how varied is still rough. To turn these few close cases into a true understanding of the galaxy's hidden worlds will take new instruments, ones now being built and prepared, that promise to count and examine the wanderers as never before. WISE 55 is the nearest example of its kind that we can study in detail today, but it is only the beginning. New instruments now being built and launched are designed to find and examine cold, starless worlds in far greater numbers, and they will turn the lonely giant in Hydra from a rare curiosity into one member of a well-mapped population. The coming years promise a kind of census of the dark. One of the most important is the Nancy Grace Roman Space Telescope, a large observatory being prepared by NASA for launch in the coming years. Roman is built in part to carry out a vast survey using the same trick of micro-lensing we met earlier, watching huge numbers of distant stars and catching the brief brightenings that betray a dark object passing in front. Where earlier micro-lensing surveys could find only a scattering of free-floating worlds, Roman is expected to detect many more, reaching down to smaller masses than ever before, perhaps as small as worlds the size of Mars. For the first time, we may get a reliable count of how many starless planets truly drift through the galaxy and what sizes they come in. That count matters directly for understanding WISE 0855. Right now, we know the wanderers exist and that they are numerous, but our estimates of just how numerous swing widely. Roman's census could pin down the real number, telling us whether worlds like WISE 0855 are merely common or staggeringly so. It could also reveal the balance between small and large wanderers, which in turn hints at how they form, since worlds born alone and worlds flung out from systems should leave different patterns in the population. WISE 0855 would then take its place as the nearest known member of a properly counted crowd. Alongside Roman, a new generation of enormous ground-based telescopes is rising, chief among them the extremely large telescope being built in the Atacama Desert of Chile. With a main mirror far larger than any optical telescope before it, this giant is designed to gather faint light in extraordinary detail. Instruments of that power should be able to study cold, free-floating worlds that are far too dim for today's telescopes, examining their atmospheres directly the way Webb now examines WISE 0855. What is possible for the nearest example today may become possible for many more distant examples tomorrow. Together, these tools promise to transform the field. Roman will tell us how many wanderers there are and where they lie. The great ground telescopes, along with Webb itself, will let us study individual ones in depth. The few cold worlds we can examine now, with WISE 0855 at their head, will grow into a catalogue of many, each with its own measured temperature, makeup, and history. The hidden population sensed only through brief flickers of starlight will start to come into focus as a real collection of knowable places. WISE 0855 will keep its honoured place through all of this. It was the nearest and coldest, the first such free-floating giant we could read in real detail, the proving ground for the methods that will be used on the rest. Whatever the future surveys find, this lonely world will remain the doorstep example, the one that showed us what a sunless giant near Earth is truly like. Knowing how common such worlds may be only sharpens a quieter question about WISE 0855 itself. How long has this particular world been drifting alone? Its solitude is not just a matter of space, but of time, and the timescales involved are almost beyond imagining. We have spoken of WISE 0855 as lonely in space, cut off by light years of emptiness. But it is lonely in time as well. This world has been drifting on its own for an immense span, and reckoning how long deepens the sense of just how solitary it is. Its loneliness is measured not only in distance, but in ages. Pinning down the exact age of a brown dwarf is difficult because, unlike a true star, it has no steady fire whose burning marks the passage of time. Astronomers estimate the age of WISE 0855 only roughly, from its temperature and mass and from models of how such objects cool. The range they arrive at is wide, spanning from a few 100 million years to several billion. The truth lies somewhere in that broad window. What is clear is that this is not a young object freshly formed. It has been around for a very long time, likely for a good fraction of the age of the universe itself. Whatever its precise age, the object has spent essentially all of it cooling and in all likelihood drifting alone. If it was born solitary, then from its earliest days it has had no star, no companion, only the slow loss of its own birth heat into the dark. If instead it was cast out of some distant system, then after that ancient ejection it has wandered starless ever since, the moment of its exile lost in deep time. Either way, the solitude is not a recent thing. It stretches back across most of the world's existence, perhaps across billions of years. Try to feel the length of that. Several billion years ago, the Earth itself was young, its surface barely settling, life only beginning to stir in its oceans. Across all the ages since, through the rise of every living thing on our world, through the slow drift of continents and the births and deaths of countless generations of stars, WISE 0855 has simply been moving through the dark, cooling alone. It witnessed nothing, because there was nothing near it to witness. It just drifted and cooled and drifted on, and it is not finished. With no inner fire to renew it, WISE 0855 will keep cooling for ages still to come. It will grow slowly colder and fainter over the next billions of years, its feeble glow dimming further toward the temperature of empty space. Long after our sun has run through its own life and faded, worlds like this one may still be drifting through the galaxy, colder than ever, carrying the last traces of warmth from births unimaginably far in the past. Their loneliness will only deepen with time. There is a strange grandeur in that, a solitude measured in spans that dwarf all of human history. WISE 855 is not lonely the way a person is lonely, for a while, in a moment. It is lonely across deep time, a constant patient drifting that began before our world had taken its present shape and will continue long after. The emptiness around it is matched by the emptiness of the ages it has crossed alone. This, finally, is what gives the phrase its full weight. To call WISE 0855 the loneliest place near Earth is to speak of more than its distance from any star. It is to speak of a solitude woven through both space and time. Gathering all of this together, we can at last say plainly what that loneliness really means. We have travelled a long way to understand a single faint point of light, and now we can say plainly what makes it the loneliest place near Earth. The loneliness of WISE 0855 is not a mood or a metaphor. It is a precise physical condition, and gathering the threads together reveals just how complete it is. It is lonely in space. At 7.5 light years from the Sun, it is among our nearest neighbours, and yet that nearness is cold comfort. The nearest star to it, our own Sun, is so far away that its light arrives as nothing more than a faint point, offering no warmth at all. There is no other star close enough to matter, no companion world that we can find, not even a confirmed moon. It hangs in the emptiness between the stars with nothing nearby to light it or hold it. It is lonely in warmth. Almost every other glowing thing in the sky is tied to a fire, either burning one of its own or basking in the light of a neighbour that does. WISE 0855 has neither. It never gathered enough mass to ignite the lasting fire of a star, so it lit no engine of its own. And it circles no sun to borrow heat from. Its only warmth is the dying ember of its birth, the heat made when it first drew together, slowly leaking away into the dark with nothing to replace it. It is, in the most literal sense, a world lit only by its own fading glow. It is lonely in time. For most of its existence, across what may be billions of years, it has drifted exactly like this, alone and cooling, through ages that span nearly the whole history of our own world. Its solitude did not begin recently and will not end. It reaches back almost to the object's birth and forward into a future of ever-deepening cold, and yet, for all that, it is not beyond our reach. This is the quiet wonder at the centre of the story. A world this faint, this cold, this utterly alone, sitting in the emptiness more than 7 light years away, has nonetheless been found, measured, and read. We know its temperature, close to the freezing point of water. We know the gases in its air, water and methane and ammonia and more. We have weighed the rare atoms in those gases and traced the slow churning of its sky. From a single dim glow gathered by a telescope far from Earth, we have built a real portrait of a place no one will ever visit. If you find that you want to follow more of these long, quiet journeys into the far and the strange, you might keep this channel close for the nights ahead. That is the whole purpose here, to sit with one distant place at a time and come to know it well. There is a particular kind of marvel in this. The universe is full of lonely places, and most of them we will never sense at all. But this one, the nearest of the lost, came just close enough. It drifted to our doorstep and we were ready, with eyes that see by heat and patience enough to read its faint light. So return now to where we began, to that small glow of warmth in a wide black field. When the James Webb Space Telescope opened its eye on WISE 0855, there was nothing dramatic to see, just a faint smudge of heat among the scattered points of distant stars, easy to miss, easy to slide past. And yet, knowing now what we know, that little glow holds a whole world within it. Picture it once more, out there in the constellation Hydra, a giant of hydrogen and helium, heavier than Jupiter, wrapped in a frigid, churning sky of water and methane and ammonia. No sun rises over it, no day breaks, no night falls. There is only a permanent deep twilight, lit faintly from within by the last warmth of its making, while high in its air, water freezes and drifts and the slow weather of a sunless world turns over and over. It has been doing this alone, for longer than the Earth has worn its present face, and it is near. That is the part that stays with you. Of all the countless wandering worlds that may fill the dark spaces of the galaxy, this one happens to drift just close enough to study. The nearest free-floating world we know, the coldest of its kind ever found. It is a rare gift of position, a single example of a vast hidden population, set down almost within our reach so that we might learn what such a place is truly like. Think, too, of how faint the thread is that connects us to it. No spacecraft has gone there. No probe ever will, not for a very long time. Everything we know about Y0855 came to us as light, a thin trickle of infrared warmth that left the world and crossed more than 7 years of empty space to reach a cold telescope far from Earth. From that trickle, spread out and read with care, we drew its temperature, its chemistry, its weather, even the rare atoms in its air. A whole world, known through a whisper of heat. There is something steadying in that, something worth carrying with you into the quiet. The universe is mostly cold and mostly empty, full of places far lonelier than any we will ever stand in. Wise, 0855 is one of them, perhaps the loneliest we can name so close to home, and yet it is not unknown, not unseen, not unreachable by the patient work of looking. We found the faint glow. We learned to read it. The loneliest place near Earth is lonely no longer in at least one sense, because now, across all that dark, something is paying attention. Let that be where we rest tonight. A sunless giant drifting in the deep cold, lit only by its own slow-fading warmth, more than 7 light-years away in the direction of the water snake. It asks nothing of us and never will. But we turned toward it anyway, and we saw it, and we came to know it a little. And the wonder of that, quiet as it is, may be the truest light in the whole long story of the loneliest place near Earth.